share screen. All right. So we've got 3 sections today. We've got the latter 2 sections of chapter 3 should be review, which is nice. But let's go through them. So 3, 4, he already forgot what it's called. I think it's called more equation solving. That's what we're going to go with. More equation solving. Or, yeah, that works. There are 2 types of equations in this section that are of concern. The first one is a rational equation. And to be very honest, these are hard to create off the top of my head. So I'm going to just pull one from the textbook. I could make one up and it could crash and burn, so I don't want to do that. Because I like ones that end up being reasonable answers. I doubt I'd give you one that is a with imaginary solutions or even horribly square root solutions. Yep, nope. I've gone too far. 25 is a goober, 26 is a goober. Let's try 24. All right, let me copy it over here. So it would be 1 over 3x plus 6 minus 1 over x squared minus 4 equals 3 over x minus 2. So there's really not a lot of theory in this section and the next one. It is just pure examples. Okay, you may already know some ways to solve a rational equation. One of them is to get fraction equal to fraction and cross multiply. That's fine. In my opinion, that's a lot of work. And in this one, it really won't matter as far as the amount of work is concerned. The way I typically do it is I multiply everything by the LCD, which means we have to first figure out what that is. And the way you do that is off to the side, you'd figure out how each denominator factors. So this first one factors as 3 times x plus 2. The second one factors as x plus 2, x minus 2. And the third one doesn't factor. We would just consider it prime. It's already factored. So the LCD is the smallest thing that all 3 of these denominators would divide into. It's easier to do with numbers, but with variables it's not too bad. So what would that smallest thing be? So we have
the x plus 2 or the x minus 2.
Good, and there's something else we need from the first denominator. What else do we need?
The third.
Very good. Yeah. So this is the smallest thing that all 3 of those denominators in purple and green would divide into. So then what I would do is I would multiply, multiply each term by this LCD. Notice I am taking the time to write the LCD next to every fraction. Two reasons. One, I'm cool like that. Two, it's because I think visually and I think it's easier to see myself canceling out common terms. This is Very easy to do too much in your head and you accidentally miss a term. So for the first fraction, what cancels?
The 3 in parentheses x plus 2.
Excellent. So notice we would be left with the we'd be left with the 1, which doesn't make a difference, times x minus 2. So I'll just say x minus 2. Minus comes from here, from the original problem. The second one, second fraction, the x plus 2 and the x minus 2 cancel. So we're left with 1 times 3, which we can just say is 3. That's nice. Equals, and on the right, the x minus 2 cancels. So we are left with 3 from the numerator times 3x plus 2 from the LCD. So if you want to write down steps, step 1, multiply everything by the LCD. Step 2, solve as normal. The reason that's very vague is because when you're done, you might be left with something that's linear, quadratic, cubic typically. This one happens to be linear. So what we'll do is we'll combine like terms. We'll distribute a 9 through here. And then linear says variable on one side, number on the other. So I'll subtract 18. I'll subtract x. And in this case, we'll divide by 8. To get the pretty answer, negative 23/8. There is a step 4, and step 4 is check. Now, mainly what you're checking for is that there's no accidental division by 0. The LCD is what you can look at. Notice that positive 2 and negative 2 would cause the LCD to equal 0. And remember, the LCD came from the denominators. So as long as we don't get an answer that's plus or minus 2, we're okay. We got negative 23/8. We're good. We don't have to worry about anything. If we had gotten 2 or negative 2, then we have no answer. We'd have no solution. So when you're doing these, it might work out to where there is no answer. So definitely check, because you cannot cause division by 0. That would be bad. Okay. Do you need to see another one? All right. So that's it. Multiply by LCD, solve as normal, check. Oh, wait, that's only 3 steps, isn't it? 4, tip your server. Okay. So then the next type in this section is a radical equation. There's 2 types you might have. You might have a square root or a cube root. Square root's the most common of the types. So let's go through that type of equation. Give me a second, because I'm totally making this one up. Don't write it down yet. I'll let you know when it's safe. We'll put it, that's good there. Oh, you know what? No. No, I'm changing something. I'll tell you what to do. I like it. All right, suppose we have the square root of x squared plus 5 plus 1 equals x. Here we do have 4 steps. The first step is to isolate a radical. The reason it says isolate a radical instead of isolate the radical is because you might have more than one radical. If you have more than one, it doesn't matter which one you isolate, as long as you isolate one. So radical equals something that's not that radical. So in this case, we will, step 1, we will subtract 1 from both sides. We'll talk about why step 1 is very important. Step 2, you're going to raise both sides to a power to cancel out the radical. Again, that is quite vague. And the reason being is it has to encompass all classes, or all types. So in other words, we isolated a square root, so we'll square both sides. If we isolated a cube root, we would cube both sides. So we're going to square both sides. On the left-hand side, what happens to the square and the square root? The square we just wrote, I should say.
Cancel out.
Yep. So we just get x squared plus 5. On the right, we are squaring 2 terms. On the left, we were squaring 1 term. On the right, we're squaring 2 terms. Because we're squaring 2 terms, what do we have to do?
Wouldn't that be FOIL it?
Yep. And doing so, you would get x squared minus 2x plus 1. Step 3 does not apply for this problem. Step 3 would be repeat steps 1 and 2 if there are more radicals. But we're good here. We only have the 1 from the beginning. And step 4 is solve as normal for the big part and check. What type of equation do we have from step 2? Very good. We have a quadratic equation. So a quadratic, one of the 4 ways to solve it would be to get everything to one side. But notice in getting everything to one side, what happens to the x squareds?
They end up canceling out.
Yep. So these are gone. So we went from a quadratic down to a linear. So I'll subtract 1 from both sides and divide by -2. So now let's check our answer. If I put negative 2 into the original equation, always go back to the original. Is this true? So negative 2 quantity squared is 4, plus 5 is 9, square root of 9 is 3, plus 1, does that equal negative 2? Nope. Bum, 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 bum. So negative 2 is an extraneous solution, so we actually have no solution for this problem. The extra solution was created by squaring both sides. Multiplying by an LCD or squaring both sides can create extraneous solutions. Okay. That is, yeah, that was 3.4. It's light. And 3.5 is also very light. Questions before you mosey on? Okay, let's mosey. 3.5 is, oh, that's right, yeah, there it is. 3.5 is absolute value equations and inequalities. We're going to first start off with absolute value equations. And the key thing is, if an absolute value of x is equal to a number a, then there are two possibilities. Then either x is equal to a or x is equal to negative a. That's the big thing you need to know for an absolute value equation. So basically what happens is you turn your absolute value equation into two minor equations. So let's do a light one first. So let's suppose we have the absolute value of 5x plus 7 equals 12. Oh, yeah, we'll make it 12. The one thing that has to be true first is that the absolute value is all by itself. In this case, we're good to go. We're not multiplying it by anything, subtracting, adding anything to it, dividing anything into it. We just have absolute value of something equals number. Great. So because of that, what happens is the first breakup says that the inside, in this case 5x plus 7, is directly equal to the right-hand side. And the second one says that the inside is equal to the negative of the right-hand side. So we turned our absolute value equation into two linear non-absolute value equations. How would you solve for x in both equations?
Subtract.
And then?
After we subtract, we gonna then divide.
Perfect.
No.
Yep,
Yeah,
that's it. That's it.
divide.
Excellent. So the first one would give you 5x equals 5 by subtracting 7, and then dividing by 5 you get 1. Second one gives you 5x equals negative 19, and dividing by 5 you get negative 19 fifths. And these are both good to go. The only other hitch this could possibly take, really, is if it weren't isolated first. So let me make one up real quick. Eh? Oh, there is another hitch. I forgot about the other hitch. But we'll get to that in a second. Let's suppose we had 3 times the absolute value of x squared minus 1. Minus 2 equals 10. One mistake students make is they distribute through an absolute value. Sometimes it works, sometimes it doesn't. Do not confuse absolute values with parentheses. So I would not want you to distribute the 3 through. Instead, I'd rather you get rid of it. But working outside in, we have to do what to that 2?
Add it to each side.
Yep. Excellent. So if we did that, what number is on the right-hand side?
4, right?
Yep. Boop. So again, not really steps here. Step 1, isolate the absolute value. So now that you have absolute value equals number, break it up into 2 pieces and then solve each piece, please. I'll give you a couple minutes. Give it a try. So as your first step, you should have broken it up into two pieces where the inside of the absolute values equal 4 and then also negative 4. Questions on that? Okay, so for both of them, we're going to add 1. So we'll have x squared equals 5. And then we take the square root. What do we get? Anyone?
You get negative 5.
Careful. So x squared
5.
equals 5. We have to get rid of that square. How would we get rid of that square?
Would you divide?
No.
Square root of 5.
25. What square root of 5? It's 5 is 5.
Joby, one more time.
Square root of 5.
One more time. Are you looking at... Can you see my
Plus
video?
or minus the square root of 5.
There it is. So when you square root an equation, you have to include a plus or minus. Don't square both sides, so don't get 25. We have to get rid of the square by taking the square root of both sides. Good. The right side equation, same process. We're going to add 1. Take a square root of both sides, include a plus or minus. Ugh. How does the square root of negative 3 clean up? So go back to section 3.1. Boop, 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 boop.
Wouldn't that be I?
Yeah. Plus or minus the square root of 3i. So isolate, break up, solve as normal. Not too much to check for these, to be honest. You should always check, and it's going to be the point of the next problem we talk about. But generally, these work out pretty okay. So with that, I would like you to solve this by just looking at it. So don't even break it up. Just solve it just by looking at it. The absolute value of 7x plus 1 equals negative 8. And what's your gut instinct here?
X equals 0.
So if we put in 0 in for x, and inside the absolute values we get 1. Absolute value of 1 is 1. How is this problem different than the other two?
The 8 is negative.
The 8 is negative. Can the absolute value of anything equal something negative? No. Remember, absolute value tells you distance from 0. You can't have a negative distance. In this class, in trigonometry, that's something else. But here, because the isolated absolute value is equal to something negative, this one has no solution. So if that ever occurs on your homework or on the test and you literally straight up write no solution with nothing else, that's correct. If you did break it into two pieces and then solve for the variable and then check that answer, it will not work. Again, because it doesn't matter what's in these parentheses, what's in these absolute values, because as long as it's got a variable. So it could have been crazy in there. It could have been x to the fourth minus 5x squared over 2x equals negative 8 in absolute values. Doesn't matter, no solution. Okay. Questions on absolute value equations. Okay, let's talk about absolute value inequalities. We have two types of inequalities, major categories, I should say. You have or, and you have and. An or situation is when the absolute value is greater than or equal to a number. An and situation is when the absolute value is less than or equal to a number. I usually like to solve these graphically. The book will show you a different approach, so if you don't like the graphical approach, please reference the book. You cannot make the distinction of it's and or until the absolute value, the initial one, has been isolated. Because during the isolation process, remember the inequality can flip if you were to multiply or divide by a negative number. So, for example, let's say we had 2 times the absolute value of x plus 1 minus 5 is greater than, I don't know, 4? Nope. 7? How can I make that into a 7? Nailed it. You can't even tell I made a mistake. So we will isolate this absolute value by adding 5 and then dividing by 2. What number would we get on the other side?
Six.
Yep. So step 1 as before, isolate. Step 2 is before, break into 2 pieces. Asterisk with caution. So the first piece is like you never had absolute values. X plus 1 is greater than 6. The second piece has a negative involved. What happens here is the x plus 1 will stay x plus 1, but you have to flip the inequality now and then change the other side as well. So because you're negating, or you're technically multiplying through by -1, the inequality flips for the second piece. And now we solve as normal. So for both of them, we'll subtract 1 So we'll get x greater than 5, x less than -7. And we typically write our answers in interval notation. To get that, what you can do is you can draw a picture. So for instance, x greater than 5, here would be 5. We want greater than, so parenthesis, and we would want everything to the right. X less than -7, here's -7. It's strict, so parenthesis, and we want everything to the left. The conjunction here is the word or, because our inequality after being isolated was greater than. So it's if we're going to put both of these on a single number line. So we would want everything to the left of 7 or everything to the right of 5. And then this in interval notation would be -infinity to -7, union, parentheses, 5 to infinity. So typically when you have an or, your sets are disjoint, meaning they don't overlap. So it's basically this union this. When you have an and, I'm just going to make this up. Let's suppose we have x greater than or equal to 3 and x less than or equal to 8. When you have an and, you typically have an overlap. So if this were 3 and we want greater than, we would want to the right. And if this were 8 and we want less than, we would want to the left. So and says where do they overlap each other, and they overlap between 3 and 8, including the 3 and the 8. So the ors you typically write as 2 disjoint set, and you typically write as 1 set. Okay. Questions? Muy bieno. All right, that is chapter 3. Okay. So now we move on into 4.1, which is polynomial functions and models. Unfortunately, sorry-ish, we get very theoretical. 4.1 is a little heavier of a section, so we'll do examples when we can, time permitting. 4.1 through 4.4 builds, so it's actually very good that your midterm is now stopping at 4.4. because 4, 5, and 4, 6 are completely separate. So it's good that we take a break before hitting that stuff. We start off with probably the ugliest definition of the entire class. So, sorry? Here it is. A polynomial function is of the form okay, before I write this down, I need everyone to think about a happy thought. Maybe a Cracker Jack box with 2 prizes inside. That'd be amazing. Everyone knows that. Whatever you know, hold on to it. You ready? All right. F of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus dot 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 plus a sub 1 x plus a naught, or also known as a sub 0. So you'll notice that the subscript matches the exponent. That's all that says. We got more to write where a sub n minus 1, a sub n minus 2, dot dot dot, a sub 1, a sub 0 are real numbers. And n is a whole number. All right. I need everyone to unmute themselves and give me a real number.
8.
Keep going.
5.
Yep.
2.
Yep.
4.
Thank
7.
you. All right. Now give me, well, you guys gave me very boring real numbers. I'm going to make this 5/5. Ooh, fancy. I'll make that 2 -2. Give me some whole numbers now. I already heard.
23.
Ooh, that's very fancy. I need some more. I need one more.
10.
Works for me. So we've created the function f of x is equal to 8x to the 7th plus 5/3 x to the 23rd minus 2x to the 10th plus 4. Congratulations, that's a polynomial. So as long as your coefficients are real, that's what this says, and your exponents are whole, you've got a polynomial. Things that are not a polynomial would be if, for instance, you had imaginary coefficients, or if you had fractional exponents, or negative exponents. These are not polynomials. You can't have that with a polynomial. Coefficients have to be real. Exponents have to be whole. So looking at our polynomial in purple in the bottom middle there, bottom middle, what exponent is the highest?
The 23.
Very good. So we call the 23 the degree. The degree is the highest exponent within a polynomial. The corresponding term that has the x to the 23rd is 5/3 x to the 23rd. That term is called the leading term. It is sort of a misnomer here because leading tends to mean first. Well, notice because addition is cumulative, you don't have to write the polynomial in what is normally called decreasing degree. We tend to write our polynomials in decreasing degree, meaning we would have written this as 5/3 x to the 23rd. Then the next highest exponent is 10, so minus 2x to the 10. Then the next highest exponent is 7, and then the constant is 4, and that's last. So we like when our leading term is first, but it does not have to be. The coefficient of the leading term in this case is 5/3, and we call that the leading coefficient. Oh, now I have to remember to spell it. I did it. Did it. Gonna give myself a sticker afterwards. There we go. Next words. All right. It says you did it. Okay, questions on these three terms because they are huge. All right, the build up from section 4.1 to 4.4 is to learn how to graph a polynomial function with little to no use of the calculator. You don't learn how to do that completely until calculus, where you learn what the calculus is telling you of how to find high and low points, things like that. If you remember, we called them relative maxes and relative mins in the previous chapter. So we're going to find other things, and there's bits of information from the polynomial function that tells us what the graph looks like. Mainly, the leading term tells us a lot. Before we get to that, let's talk about the graphs of polynomial functions.
I have a question.
Go for it, please.
The polynomial we just did, so that was the answer, or we still have something to solve for it?
Nope, we're not. That was just extracting out more terms: degree, leading term, leading coefficient. We don't have an equation, so we have nothing to solve for.
Okay.
Yeah, that was just to say, hey, these numbers are important. Other questions? Okay. So before we say what a polynomial function is, we're actually going to say what it isn't. The graphs of polynomial functions do not contain the first thing a polynomial function's graph does not contain is a jump. A jump is a sudden change in a y value. The next thing it doesn't contain is a hole. A hole is a missing point. The third thing it doesn't contain is a gap. A gap is a bunch of x values that are missing. All three of these have something in common, which we'll talk about. First off, does anyone know what we call it when the graph's gap, if there's a gap and it's very small? We call it a baby gap. I'm kidding. That's not real. Don't write that down. All three of these are examples of discontinuities. Discontinuities. Meaning that there's some form of break. There's actually another discontinuity that we could talk about. There's no asymptotes. Now, a horizontal asymptote you can't have, but the one that would be considered a discontinuity would be a vertical asymptote. Oops. So I should add that to my repertoire. You can't have any vertical asymptotes. Yep. You're just making up that graph. Okay. The next two are also related. Graphs of polynomial functions do not contain cusps. A cusp is a point created by two curves. A sharp point created by two curves. And the last one is a corner, and that's a sharp point created by straight edges. Cusps are rare. I like to talk about them because that symbol is a symbol for an Aries, which is the best zodiac symbol, as everybody knows. Corners, notice that's the graph of an absolute value function. So absolute value functions are not polynomials. These two we would call not smooth. So putting these together as far as what a polynomial's graph is, the graph of a polynomial function is smooth, so no sharp edges, and continuous, no breaks. The graph of a polynomial function is smooth and continuous. So as I said, in the next few sections, we'll be graphing polynomial functions completely. So make sure you do not create any of these 6 things in your graph, because then it's definitely not correct. Okay. So first thing that we can talk about is where arrowheads will occur. And the thing that tells you where your arrowheads are is actually the leading term. So this is called the leading term test. There are two types of degree. You can have even degree, or you can have odd degree. And to be specific, odd is at least 3. The reason we discount 1 is because 1 is linear, which is its own little beast, and we covered that already. When you have an even degree, the arrowheads point in the same direction. When you have an odd degree, the arrowheads point in opposite directions. If you ever forget that, just think about the most basic two. This is y equals x squared. And this is y equals x cubed. Oh, that's terrible. Don't look at that. Oh, that's even worse. That is slightly better. So even point in the same direction, odd point in opposite directions. However, remember that the leading coefficient also plays a role. If positive, there is no reflection. But if negative, it's reflected over the x-axis. Which is what we did at the end of chapter 2. So let's put some stuff together here. You know what? Let's make a chart. I want to make a chart. So we'll say degree even, degree odd, and we'll say positive leading coefficient, and negative leading coefficient. So there's 4 cases. Ooh, can I zoom? Zoom in. It's happening. Now how do I do this? Oh. Alright, that's better. The first case is if your degree is even and your leading coefficient is positive, then your arrowheads are pointing up. And you'll end up in quadrants 1 and 2. The reason there's dots in the center is because we don't know what happens in between the arrowheads just yet, but the leading term will tell us where the arrowheads are, and they have to be in quadrants 1 and 2. If your degree is even, they still point in the same direction, but now if your leading coefficient is negative, that direction is now down. So your arrowheads end up in quadrants 3 and 4. If your degree is odd, the arrowheads point in opposite directions, but if the leading coefficient is in positive, there's no reflection, which means your arrowheads end up in quadrants 1 and 3. So notice it starts negative but ends positive. However, when the leading coefficient is negative, that flips. So your arrowheads end up in 2 and 4. So let's suppose I had this graph. If you suddenly want Arby's, then it's working, so that's good. Tell me about the degree. The degree has to be
Even.
even because the arrowheads point in the same direction. Good. Tell me about the leading coefficient. The leading coefficient has to be
Negative.
very good because it's been flipped. So if I gave you that graph and I said, give me an example of the possible leading term, as long as your leading coefficient's negative and your degree is even, it's a correct answer. So if you wanted to say negative 4x to the 6th, cool. That's correct. This is negative. This is even. Infinitely many answers. So questions on how the leading term relates to the degree. Oh, I'm sorry. How the leading term relates to the arrowheads. Okay, very good. All right. Okay. Again, this section is just setting the stage for other stuff. So if it seems like it's random, it's because it's random. We're going to delve much deeper and start to put concepts together as the chapter progresses. The next idea is that of a zero. A zero, I'll just write it this way. C is a zero of the function f if f of c equals 0. So any number, real or imaginary, that if you put it into the function and you get 0, we call that number a 0. If it's a real 0, then you've actually also found an x-intercept. Imaginary zeros can't be graphed, so it doesn't affect the graph. So for example, if I had f of x is equal to x squared plus 6x plus 8, and I wanted you to find f of negative 4, you would do negative 4 squared plus 6 times negative 4 plus 8. And what do we get? He wonders.
0.
0. Who said that, Joby? Right.
Yeah.
Do you have a hot pink notepad? If you do, you can write a "You did it" sticker, and you can wear it for the rest of the class if you want.
I don't, but I should probably buy one.
Let's go back. Why don't you have one? Everyone else has one. Everyone nod their head. Yeah! Ah, good job, Charmaine. I'm so proud of you. All right, so we just found the number that makes the function equal to 0. So we would say -4 is a 0 of f. Hooray. And if we stuck on another number like 5, we wouldn't get 0. So you would say 5 is not a 0. The big process over the next 4 sections is to find zeros, because as I said, real zeros are x-intercepts, and if we know where the arrowheads are and if we know where the x-intercepts are, we can sketch a graph. So this is where we're headed to. So this one happened to be factored, and I gave you a number to find the zero. This one happened to be expanded, and I gave you a number, and it turned out to be a 0. Let me give you another one that happens to be factored. So let's suppose we had f of x equals x plus 1 squared times x minus 3 cubed times x minus 5. So looking at this function, what numbers would cause the function to equal 0? So what number would you put in for x and the whole thing equals 0?
Would it be -1?
Yeah. -1 would make this first factor equal to 0. And then 0 times anything is 0. So that cancels out everything. What's another number?
Three and five.
3 and 5. Awesome. Good. Related to your zeros is the concept of a multiplicity. Multiplicity is the number of times a zero's corresponding factor appears in the factored form of the polynomial. The multiplicity is the number of times a zero's corresponding factor appears in the factored form of the polynomial. It seems like a very heavy definition. It's not too bad. So x equaling -1 corresponds to the factor x plus 1. And notice x plus 1 has a square on it, which means it appears 2 times. So we would say -1 has multiplicity 2. Likewise, x equals 3 corresponds to the factor x minus 3. X minus 3 appears 3 times. So we would say 3 has multiplicity 3. And what's the multiplicity of 5? How many times does its factor appear?
Once.
Once. Excellent. Because even though it's not written, there's technically a 1 up there. Great. So show and tell time, because they're okay. I don't know what's going on there. Oh, that's even worse. All right, there we go. What I'm going to do is I'm going to plot or graph this function. You don't have to do this. This is just show and tell. So I hope everyone brought their carpet squares. And their cocoa. Cocoa will not be provided. So I'm just gonna hit. I'm just gonna graph this real quick. Oh, that's not what I wanted to happen. Okay, let me. Oof. I'll make that 7. Okay, that works a little bit better. So notice in the graph we can see it crossing. I'm sorry. We see some interaction happening at -2, or -1, excuse me, and we see some something happening at 3 and 5. So I want you to try to generalize here. It's a little bit of a jump. Something happened at -1 that was different than what happened at 3 and 5. What did the graph do to the x-axis at -1 that it didn't do at 3 and at 5? So notice to the left of -1, it's above the x-axis, and to the right of -1, it's still above. To the left of 3, it's above, but then to the right, it's below. And then notice at 5, it's the opposite. It went from below to above. To generalize this, I'm going to minimize this real quick. To generalize this, when the multiplicity is even, the graph touches the x-axis. We're almost done. I apologize. So that's what happened at -1. It touched the x-axis. Meaning to the left and to the right of that value, the y's have the same sign. In this case, they're both positive. However, when you have odd multiplicity, the graph crosses the x-axis. So at -1 we had a touch, and at 3 and 5 we had a cross. So, to recap, arrowheads were told to us by the leading term. We now know that if we know where the zeros are and their corresponding multiplicity, we know if the graph will touch or cross. So with those bits of information, we can sketch a graph. And that's what 4.2 next week, that's what we'll do. However, it depends fully on, is the function factored? If the function was not factored, we'd have to factor it first. Now, in your intermediate algebra, you learn some factoring techniques, but if you have a 5th degree polynomial, techniques go out the window. You can't use any of those. So that's what we're leading up to, is what happens if we have a higher degree polynomial, how do we factor it? That's what we learn in 4.4. Next week is going to be heavy. Unfortunately, we end, the middle of this chapter is very heavy. I would definitely recommend pre-reading 4.2 and 4.3. 4.4 is heavy. It's got a very big theorem in there. But if you pre-read 4243, you'll get a lot more out of the lecture, please, if you're not already doing that. All right, that's enough torture for today. Have a great pink Post-it note evening, and I will see all y'all next week. And I will set a reminder to post this video. I